because I'm sure people will find like literally the most ridiculous gifs of all time. Okay, let's find our derivative. Oh, you know how hard it is to bounce back and forth between derivatives and integrals? Yay, okay, so this is going to be 6x squared plus 12x minus 18. That's this one. Boom. List any critical values. So let's set this equal to 0. Let's divide everything by 6. And does this factor? 3 and 1, both of those need to be... No, one needs to be positive and one needs to be negative. So we have x equals 1 and x equals negative 3 as critical values. Let's go ahead and put them onto our number line. And we're going to find our intervals of increase and decrease. So let's test x equals 0, let's test x equals 2, and let's test x equals, negative 5. We already have factored form. Factored form is x minus 1, x plus 3. So all we really want to do is sub these x values, these test values, into these two factors and see what happens. So if we take negative 5, that would be negative 6, and that would be negative 2. So this should be overall positive because both of my factors are negative. For 0, we have negative and positive, so overall negative. And for 2, we should have positive, positive. Boom. So now I'm starting to get the picture of what this function looks like. Positive to 0 slope to negative to 0 slope to positive. This is also indicating to me that there should be an inflection point probably somewhere in here. There's probably going to be an inflection point. Okay, but I can generally see the concavity too, right? I kind of generally have a concave down, and I generally kind of have a concave up region, just based on this preliminary analysis. So we can get a lot of stuff done just with the first derivative. Intervals of increase are happening from minus infinity to negative 3. And then from 1 to infinity. I'm not including the endpoints because technically the derivative is not increasing there. It's technically 0 there. And the intervals of decrease are going to be everything in between. So from negative 3 up to 1 should do the trick. So that's our full first derivative analysis. Okay, let's take a look at f double prime. So f double prime is going to be 12x plus 12. Let's set that equal to 0. And it looks like we're going to get negative 1. So negative 12 over 12 should be x. So we have one potential place. So here's our solution, right, for f double prime. Use parts B through E to identify maximums as points. What does that mean? Okay, so there's a potential maximum at negative 3 and a potential minimum at 1 is what they're saying. Got it. Okay, I understand. I think I get what they're trying to say. What's our original function? We basically just have to sub 1 into this function and negative 3 into this function, and that'll work, I think. So we have a function that looks like this. Let me just readjust some stuff like so we can see that there are two maxes and mins here, right? Got one at negative 3, 0, and one at positive 1, negative 64. So to get these values, we would just plug these critical numbers that we had. So we went through all this process to find these two critical numbers. If I plug those critical numbers back into the function, I'm going to get a pair. And this analysis up here is going to tell me those points where we have a max or a min. So f at 1 is negative 64. That's this one here. And if we look at our first derivative test, we know it's happening down here. So it's got to be at our min. So that's all I'm kind of using here. So identify minimum. So the minimum happens at positive 1, negative 64. And then the other interesting point was at -3. Desmos is saying this should come out to be 0. So again, we're just going to plug in -3 into the original function. We can see that the y-coordinate of 0 pops out. So -3 and 0 is going to be where we have our maximum. Use the second derivative to identify intervals where fx is concave up and concave down. I don't usually use the second derivative test. I mean, for polynomials, I already know exactly what that behavior looks like. It's concave down, inflection point, concave up. I don't need to do any more analysis with the second derivative since there are no asymptotes or other weird pieces of my function that are going to make things a little funky. So we know our inflection point happens at -1. So we know we should be concave down from -infinity to -1. And then we should be concave up from -1 to +infinity. And then use the second derivative to find any inflection points. Our inflection point happens at -1. So again, let's just pop -1 into Desmos. And my output is -32. So that's going to happen somewhere in here. We're going to get our inflection point. Desmos won't be able to tell me where that inflection point is. So I do have to plug that back in to get it. So -1 and -32. Does that, please tell me that ends this question. Holy cow. Upload a sketch of the function. Here it is. It's right here. Okay, friends, let's do some basic calculus. What day is today? Is today Sunday? Oh, Pixel Pen? Fine, you can see me. I was trying to stay incognito. Let's find the derivative. So the derivative of our numerator times the denominator minus the derivative of the denominator times the numerator, all over the denominator squared. Bam. That is our first derivative. So that's literally what I would just put right into that box. We need to find the critical values. The critical values happen when the derivative is equal to 0. And specifically, this is going to happen when the numerator is equal to 0. I'm going to, I guess, kind of just maybe make a note to myself that 3 is kind of important. And 3 is probably, I can kind of see it up here, is probably going to be an asymptote. All right, let's take a look at the numerator of our fraction. I'm going to grab this information. Let's expand. So 2x squared minus 6x minus x squared plus 1. And we're going to drop that denominator of x minus 3 squared because we don't really need to consider that when we're doing this kind of solving. So what do we got? We got x squared minus 6x plus 1. And that looks like it's factorable into, maybe it's not. No, that's not factorable, is it? No, multiply to get 1 and add to get minus 6. That doesn't feel like it's factorable at all. Does this have a solution? Is this a no solution kind of quadratic? Negative b plus or minus b squared minus 4 times a times c. No, it's solvable. All over 2a. So we just get root 30. Oh, these are gross. 6 plus or minus root 32 over 2. Blech. I guess at least I could pull a 4 out. So we could maybe go 6 plus or minus 2. I'll keep the 8 there and do something like this. So we guess we could get 3 plus or minus root 8. Which I guess isn't that bad, but it still sucks. So we have 3 critical values. We have 3, And then we have, what do we say, 3 plus or minus root 8. So there's 3 critical values. This asymptote is theoretically a critical value. We have to get all 3 of these critical values on a number line and kind of figure out what's happening in and around those values. So one of those is x is equal to 3. Oh, I see. One is 3 plus root 8, which I guess is a little bit bigger than 3. And then we have x is equal to 3 minus root 8, which is a little bit smaller than 3. And then it's up to us to try to get some values that are kind of in these intervals. I am going to put a big X here because I know that my function's not defined here, so there is a vertical asymptote, actually. So maybe I'll just plot that in. This is a vertical asymptote. What is 3 minus root 8? What is that as a decimal number? So we're looking at about 0.17. So we can take x equals 0 here. We can take x equals 1. And if we go plus root 8, what do we get? Like 5.8. So we can take like x equals 4 and maybe x equals 6. So those can be test points that we can use for the first derivative. The first derivative is a little messy. We did simplify the numerator though. So we could take this simplified numerator, which is x squared minus 6x plus 1. And it was over x minus 3 all squared, right? I'm going to probably do a little bit of this work on Desmos. I think it's just going to be a little bit faster than using my calculator, to be honest. And like, I'm pretty sure the last question that we did from this chapter was like 30 minutes long. And I was just like, oh my God. I wonder why everyone's always mad at calculus teachers. They're assigning too much stuff. Stop assigning so much stuff. Okay, here's our function. Here's what it looks like. Let's evaluate f at 0. F at 0 is 1/9 by the looks of it. F at 0, but that's a positive sign, so let's put positive. X at 1 is -1, so a negative sign. So f at 1 is negative. What do we need? F at 4, I think, is also negative. Are there... Where are my... Does this actually have maximums? Does this have critical values? Or am I tripping? Am I tripping? Did I make a mistake? This feels weird. This doesn't feel right at all. Yeah, exactly. It's like, I have the calculator. I know that I can do it on the calculator, but it's going to take me. It feels like it just takes me so long. Did we do this properly? Derivative of the top times the bottom minus the derivative of the bottom times the top. Expand to get 2x squared minus 6x minus x squared plus 1. We're going to take that equal to 0. Oh, what did I do? No, 2 minus 1, right? Minus 6 plus 1, yeah. Negative b plus or minus b squared minus 4ac. I think this seems fine. It's just weird that I'm not getting any critical numbers. Like critical numbers in the sense that like usually we'd be able to see them on Desmos, right? Like I feel like I'm tripping right now. I'm not seeing a... Oh, it's because I plotted the derivative. Ha! I'm an idiot. I was like, why am I not seeing these stupid critical numbers?
Oh my God. You're an idiot.
So my analysis here is fine, but we should be looking at the original function, right? So I should be having f So I need this. Just go away. Is it x squared minus 1? Oh, there's the rest of it. Yeah, okay. Now I can see my critical numbers. There's like 1 right there and 1 right there. Cool. So I'm okay with that analysis. I'm going to have to edit that a little bit, but that analysis seems fine. It's going to give me the following kind of information. I'm going to like pop up, hit a critical number, pop down, and then we're going to pop down, hit a critical number, and pop back up. So it's going to look like it's going to be a bit of a weird looking function, but we do have some intervals of increase and decrease. So our increases happen here and here, and then our decreases happen here and here. So what do we got for increase? We're going 0 to this thing, and then this thing to, negative infinity to this thing. So let's see. I'm just going to write them down here. So increasing, we're looking at minus infinity to 3 minus root 8, and then we'll union that with 3 plus root 8 up to positive infinity. And then for decreasing, we will start at our 3 minus root 8 and go to 3, and then 3 up to our 3 plus root 8. That should work for increasing, decreasing. Now, with regards to concavity, I can kind of see what the concavity looks like just with the first derivative. I probably don't really need to do a second derivative chart here. I can see it pretty clearly that we have concave down in here. This is all concave down, and this is all concave up. So we can probably even answer the concavity question and say we're concave up from minus infinity to 3. I lied, that's concave down. And then we're concave up from 3 to positive infinity. So I can kind of see that action just through the first derivative test. And this is a special case because the point of inflection is actually this vertical asymptote. So I don't need to find a point of inflection here. And in fact, I bet we won't find one, right? If we take this second derivative and we try to figure out where there's a point of inflection, I bet we won't be able to find one. But let's see what the follow-up questions are online anyway. So find the second derivative, and try to classify some stuff. So it doesn't even ask me for points of inflection. Oh no, it does, way down here. Okay, cool. So let's see if we can kind of answer some of these follow-up questions. Okay, we've used the first derivative, but I feel pretty comfortable with our intervals of concavity. State any vertical asymptotes. We know that our vertical asymptote happens at 3. And so the last thing we might be curious to get are these kind of maxes and min points. So again, I might just kind of pop back over to Desmos, and I might say, can you please evaluate f at 3 plus, square root 8. Right, and that'll give me a rough decimal approximation of where this intercept is. I can also just click on Desmos, and it'll give me the intercepts as well, right? So there you go. So we have like 11.65. This one's going to be kind of awkward to write down, but that's how we would do it. So has a maximum of blah. So the maximum happens when, no, it has the minimum happens when we're at 3 plus root 8. And the max happens at 3 minus root 8. This one was like 11 point something, like 11.66. Like 11.66. And then our max was, it feels weird to say that, but it's a local max. Our local max is at about 0.34, 0.34. Now, let's go ahead and find the second derivative just to verify that we don't have any inflection points. It doesn't look like we do on the graph, but, let's just check anyway. So the derivative of the top, 2x minus 6 times the bottom, minus the derivative of the bottom, is 1 times the top, all over the bottom squared. Now, if we want to set that equal to, so this would be kind of what we want to I would just literally just put this in for the second derivative, to be honest. I would just program that in and not care too much. But let's go ahead and try to simplify if we can. What I might do is I might do a cancellation of a one of these, so I don't have to worry about that extra factor when I go to expand. And then we're going to get something like 2x squared minus 6x, minus 6x minus 6x plus 18 minus 2x squared plus 12x minus 2. Oh, that's cool. So we get that and that disappears, that and that disappears. Oh, okay, so now I can see that there are no inflection points because we just get, we get 18 minus 2. We get 0 is equal to 16, so we get no inflection points. That's kind of what I thought might happen. So that was a nice little verification. Use a secondary to find any inflection. So none. I don't know how you would put that into that. Just leave it blank? I don't know how you would do that. State any slant asymptotes. Oh, how do we do slant asymptotes again? Is that long division? Do people even ask their students to do slant asymptotes? How do I do this? Do I have to do x squared minus 1 divided by x minus 3? Slasymptotes? Let's see what happens when we do long division. And maybe I'll put a little placeholder here. Oops, this should be a minus 1. So we would need a singular x to get up to x squared, and then we need a subtraction of 3x. And that should be that. So it should be 0 plus 3. So 3x minus 1. And then we can do a plus 3. That should get us to 3x minus 9. And we'll get negative 1, so 9. This will be 9 take away 1, which is 8. So we could say that x squared minus 1 over x minus 3 has a whole portion of x plus 3 plus a remainder of 8 on x minus 3. So this means for very large values, of x, we have that x squared minus 1 over x minus 3 is going to be approximately looking like x plus 3. So that must be our slant asymptote. Let's take a look. So there's our vertical asymptote. Boop. And then y equals x plus 3. There is our slant asymptote. Cool. So I guess it's just a limit kind of problem, right? So like as the x values get really, really big, this green function is going to get closer and closer to this particular line. And it's all based on this kind of quotient remainder relationship after doing the long division. So yeah, okay, that's kind of cool. That makes sense. I wasn't expecting to have to solve for slant asymptotes tonight, though. Oh my gosh. All right, let's pop off some derivatives and find some critical values here. So if we're looking at the first derivative, we got 3x squared minus 12x, and our second derivative should be equal to 6x minus 12. I think I'm going to go ahead and just do the critical values for both my derivatives right off the bat. We'll probably need these anyway. All right, so for second derivative, we get 12 over 6 is equal to x, which would imply that x is equal to 2 as a potential inflection point. What do we got to do here? We got to factor maybe like a 3x out. That's going to give us x take 4. So that gives us two potential candidates for maxes and mins, because this is a polynomial. So note the intervals are entered in the format blah, 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 blah. Okay. Let's see what kind of follow-up questions they got for us. All right, so we're working with a basic cubic polynomial. The basic cubic polynomial is going to look something like this. We have already found information about what's happening here, here, and here. We know that at 0, we're going to have a max, 2 is going to be our inflection point, and 4 is going to be our minimum. So we're pretty much good to go. We don't even need to do a table, to be honest, because this is a nice, easy polynomial cubic function to work with. So for increasing, let's see, we're going to be increasing from minus infinity to 0, and then 4 to infinity. And we're going to be decreasing between 0 and 4. Where are we concave down? Well, we're going to be concave down in here, and then concave up in here. So concave down is going to be minus infinity to 2, and then concave up from 2 to positive infinity. What is the limit as x approaches infinity? Well, that's just going to be positive infinity, and as we approach negative infinity, it looks like we're tending towards minus infinity. I feel like this is a very similar story. 3x squared plus 18. We just might have a bit more to do with the factoring here, maybe? In either case, let's grab what we need, and let's set these equal to 0 so that we can get some information about what's going on. So let's set our first derivative equal to 0, 3x squared plus 18x plus 27, and then 0 is equal to 6x plus 18. Let's solve the easy one first. So that should be negative 3. So we have one inflection point potentially happening at negative 3. And then with regards to maxes and mins, I guess, can we factor this nicely? So 3x and x. I guess I should maybe divide by 3 first. That might help. That'll make it x squared plus 6x plus 9. And that'll be oh, that's a perfect square. Oh! Oh, that's fun. That's fun. So that's interesting. I think what's going to happen here is our cubic is going to come up and look like this then at 3, not negative 3. Which means we're not going to have a max, we're not going to have a min, we're basically just going to... It's going to be increasing all the time. So what I might do is I actually might do a quick first derivative test here around negative 3 just to see what's up. So I might throw in a couple of values like, I don't know, we could pick 0 and maybe negative 4. And we'll just throw that into our first derivative, which is up here. And just check the sign, right? So 3 times 4 squared is 16 plus 18 times negative 4. Plus 27. This should come out to be 0 plus 0 plus 27. So this should be positive in this region. What's the sign over here? Does this come out to be positive? 3 times 16 plus 27. I feel like that's bigger than 18 times 4. Yeah, so this comes out to be 3. So we should be positive in this region as well. So the first derivative test is telling me my function is increasing. We hit this horizontal bit, and then we go back to increasing again. So there's no action here that's going to suggest that we have a max or a min. It's actually going to be an action that suggests that we have an inflection point, I think, more than anything. So this is going to be an inflection point.
That's simple.
We're going to be
3.
concave
So
down
plus
in this
27
region and
y
kind of
just
concave up
48
in this
plus
region.
27 was 75. Keep those calculations zeta sharp.
We're increasing everywhere. So minus infinity up to positive infinity. And then, maybe you could argue that we don't want to include 3, but we are nowhere decreasing. We are concave down from minus infinity up to negative 3, and then we're concave up past negative 3. And then the last thing we want to do is maybe just take a look at some limits. Boop. So let's get some limit stuff going here, and then I think that's all for me for tonight. I think I'm just about done recording stuff. We can hang out for a few minutes if you want. What's happening as x approaches infinity? Our limit's positive infinity. And as we approach negative infinity, which will be over here, negative infinity again. So that action just comes from being able to look at your leading term in your cubic. So because the coefficient of the x cubed is positive, I know exactly what this cubic function's behavior is going to look like in the long run. So that should be good there, and that should finish up 12.4. Thank the Lord.